All right, we are recording. Let me get my slide set up. Okay, we're ready to go. Well, this is, just a second. This is Math 238 differential equations, or whatever. I know the title's on here somewhere, but I don't see it. Applied differential equation, whatever the title is. It is the 20th of February, and it is time for class to start, but the students just left to go get free food. Today was celebrating homecoming, and they provided hot dogs, hamburgers, chips, cookies, drinks out at off the end of the library. So they just left to go there, so I'm left in the room by myself. But anyway, I'll get started, and they'll be coming back pretty soon. Where we left off last time, we had done a solved a linear equation, and of course it had a one arbitrary constant in it, which then lent itself to several different solutions depending on which constant you use. And if you had, boundary values or initial values or something like that, that would help you determine which of those C you would use. But anyway, the little blurb that follows that is talking about, suppose again that the functions P and F in our original equation 2, and let me write that down again for you to so you're familiar with what we're talking about. And let me get my pen reactivated. Okay. dy dx is equal to P of x times y. Do this every time. Plus P of x times y is equal to f of x. Okay, there's your equation. Okay, now this is called a linear equation because your y has a first derivative to the first power, y to the first power, and everything else is terms of x. Okay, now we solve this using our integrating factor, and we've done that. I'm not going to go through all that again. With this function P of x and that function Q of f of x are continuous on a common interval I, okay, then the steps leading to your solution, which lead you to that integrating constant, lead you to the integrating factor and leads you to a solution. Okay, they say don't memorize it, and I by no means would ever try. Then we showed that if this equation here, did you know there was free food today?
Yes, sir.
Oh, you did.
Found out when I got here.
Okay. Well, you're welcome to go get some. The other two have already left to go get it.
I got some before you. I was sitting out in my car and I saw you walk out.
Oh, you did? Okay. All right. There you are. Stuck between two other names and I couldn't read it. I had written, just messed up. So anyway, got it. So I was going on and starting the class even though they had to go to get it. So, okay.
I need to ask, can I get you to write that letter this week maybe, or next week?
Okay. Yeah.
I don't want to forget.
Right, okay. I knew you had asked, but I can't remember.
I need a letter of recommendation from the instructor for that scholarship that Lawson State gives. That it
For the summertime?
Summer and fall.
And fall, okay.
Yes, sir.
Okay. Do you know who I write it to or anything else like that?
No, sir. I just asked in the financial aid office, and she told me I need to print it out and fill it out and get a letter to you.
Okay. Okay.
So probably.
Yeah. I'll try to get to it today. I can't swear I will. I've got to reserve a van for Friday because we're going to, in fact, I need to make that announcement too. In fact, I'll make it now since I'm thinking of it. There are some changes to my office hours this week, one day change, and that is normally on Fridays I have office hours from 7:45 until 1 o'clock. Okay? Last Friday I had a infusion, so I was at the clinic from around 6:30 until around 4:30. So I was not on campus at all last Friday. And this Friday, I'll probably be leaving even earlier. We've got math meetings down in Opelika, Alabama at Southern Union College. So we'll be leaving probably even earlier than that and probably getting back later than that. So I won't be on campus at all this Friday. The following Friday, okay, I have a doctor's appointment with my internist, it's my annual physical, which we had to reschedule because I asked them to schedule me for a Friday. They said they would, and then when it came up, they had scheduled me for some day during the week. I said, I can't, I'm teaching. Oh, well, then we'll have to reschedule you. I said, well, on Friday, and they said the next one available is in March. So I will be from 7:45 until probably 9:45 or so. I'll be at the doctor's office. It's not this Friday, but the following Friday. Yes.
Yeah. Is it the 75% off? Is it just the one? That's the one I'm.
They have several applications down there. That's why
Let's just look at it.
those are the ones from my the ones
Okay.
this one here. There's one more that I think we just said that was
I'm gonna do the one that Boston State does. If you have like a certain GPA, you'll get 75% off.
That's what Austin said?
Yes.
Okay. So I was just telling Matt that I wasn't in the office last Friday because I had an infusion, and I won't be in the office this Friday because we've got math meetings down in Opelika at Southern Union College, so we'll be gone way before 7:45 and not back until probably well after 4:30 or so I won't be on campus at all this Friday. And then the following Friday, if that wasn't enough, I've got my annual physical that Friday, and that's 8 o'clock in the morning, so I know I won't be here at 7:45. Hopefully the physical will be over with by 9, and I'll be back on campus by 9:45 or so. That's hoping. I don't know if I'll get there, but I'll hope that. Okay, so I did want to let you know that. And then one other thing, I don't know if two of you have been in my class already today, one hasn't. Either the treatment I had on Friday messed up my immune system, which it usually does a little bit, or just the fact that I was working outside all day Saturday and doing a lot of sweating because it was a nice, beautiful, warm day, and I either got something in my eye or something. I have conjunctivitis pretty badly in this eye, so right now it feels fine, but once I start staring at the page or get in the glare of the light or something, it starts hurting. So if it does and I start misreading something, just correct me, put up with it, I'll get on with it. All right, what we were saying, last time we had done example 2 on page 56, top of 57, and we saw that there was a family of curves that any of those would fit the differential equation depending on what C you use, constant you use, or what boundary condition or initial condition you use. So now this is talking about a general solution. Suppose again that the functions P and F, this is our sort of standard linear equation here, that we're going to solve using an integrating factor, and we've been doing that in the first 2 examples. And this leads to that fairly complicated looking answer, y is equal to e to the minus integral of px dx times the integral of e to the integral px dx, f of x dx, plus, it's a real complicated looking thing. They say don't memorize that, don't try to plug it in, just do the math, okay? But anyway, you get, as long as the p and the f from this basic equation are continuous on a common interval, and then you lead up to that solution, that equation 4 that I didn't write out because it's so complicated. If this equation has a solution on that interval I, then it must be given in the form of that equation 4 that I didn't write down, okay? Conversely, it is a straightforward exercise in differentiation to verify that any function of the form given in 4 is a solution for this equation here. In other words, that 4 is a one-parameter family of solutions for this equation 2, and every solution of this differential equation defined on the interval I is a member of that family. So therefore, we call that really awkward-looking thing, y is equal to the blah, blah, blah that you see at the bottom of page 55, the general solution for this differential equation on the interval I, okay? And we're going to be using that term later, general solution, and we'll go from there, okay? Now, if you have an initial condition, then you don't have the constant in there anymore. You eliminate the constant. So then you don't have a general solution, you have a specific solution. So let's do example 3, which basically is going to use these concepts and hopefully make a little more sense than all the blah, blah, blah I've been saying. So here's your equation. X dy dx minus 4y is equal to x to the 6th e to the x. Okay? That's all they've given you. Okay. Now, I probably should have left what I had on the board before I erased it up there. Is this in our standard form for what we're going to be doing? No. What's wrong with it? Divide by x, and that's exactly what we're going to do. Divide this by x, and this by x. So that then produces dy dx. I say dy dx, I write dy dy. Minus, I think that was a minus, yeah. Minus 4 over xy is equal to x to the 5th e to the x. All right. Now, I know when I do this it's going to mess things up, but that's really ugly. Okay, so let me get this clarified a little bit. dy dx. Okay. Now, based on what we've done so far, what are the two functions we try to identify at this point? What is your p of x? Negative 4 over x. Very good. And alpha of x is 5th e to the x. Very good. All right. Now, where do we go from here? Now we have the linear equation, standard form. Got it. Where do we go from here? The integrating factor, mu of x. I don't know why I started to put a 0 there. I guess I use mu naughts in other places, but that's not what I want here. Mu of x is what? E to the integral of p of x dx. Remember that? Okay. So really, the first thing I would do, and I wrote this down that way, the first thing I'd do was integrate p of x. So the integral of p of x dx is equal to minus 4 times the integral of 1 over x dx, right? And what is that, by the way? minus 4 log x. Okay. Now you don't need a plus c at this point. Here it goes. It would only be a matter of time before it started aching, and it has. Okay. Now what do we do with that? We're going to raise this to the e. But before we do that, that's your integral. Your mu of x is e to the this thing, minus 4 log x. Okay. Now, if you recall a rule of logarithms, this could be written as log x to the minus 4, right? Do you remember that? Okay. Let's see. Never can remember. I'm teaching from so many different books. I can't remember. Here we go. No, this is Laplace transform. Yeah, it may not be in this one. But you can go back and see that when you have a constant times a log, that's the log of that raised, it's sort of like the same thing. Log of xy is log of x plus log of y. This is log of, a constant in front of a log, you can raise it to the exponent. Okay? So actually, let's use that form rather than this one. And there's a really good reason to do this. This would be log of x to the minus 4. What would be the reason to do that? Logs undo exponents, exponents undo logs, right? They're inverse operations of each other. So this would simply be x to the minus 4. All right. Now what do we do with that? Okay. What we're going to do, if you remember the process here, you multiply this through by everything on both sides. Okay? And this would be x to the minus 4 dy dx minus 4, and this is x to the minus 1, and we're multiplying by that 4 over x to the 5th. You buy that? Okay. Times y is equal to, and x to the 5th times x to the minus 4th will just be x e to the x. Got it? Multiply everything on both sides by that integrating factor. Now, here's what you note. You note that this thing right here is d by dx of a product of x to the minus 4 y. I think that's it. When in doubt, stop and take a derivative. No. Yeah, it is. Because you take the derivative, this is y. That looks like a dy. It's not. Okay. Okay. Now let's stop and see. Product rule. Derivative of a product would be the derivative of this would be minus 4x to the minus 5 times y plus x to the minus 4 times dy. That's it, right? So yeah, that's exactly what we've got there. So that is equal to x e to the x. right? Now, less, write that as a differential. D of x to the minus 4y is equal to x e to the x dx, and integrate both sides. Right? All right. I need more room. Okay. The integral of a differential, again, those are operations that are inverse of each other. So that just yields x to the minus 4th y. The integral of a derivative is that, okay? Equal to, now we do the integral of this. Now that's going to take a little bit of work, not much. How do we integrate something that looks like that? This right here. It requires one of those techniques we learned in Cal 2. Techniques of integration. By parts, exactly. And which would you let be what? Let u equal something, and dv equals something, and then du, and then v. Yo! What do you think the u will be? Do the u to be the part that's going to get simpler when you derivative, and leave the dv to be something that doesn't get any worse when you integrate. And e to the x doesn't change, so let that be that the dv be e to the x dx. So this will make this just x. And if u is equal to x, what's du? 1 dx, okay? And then integrate the v, and what do you get? E to the x. Okay, now what do you do with that integration by parts? How does that run? You multiply the u times the v, and that's going to be, so this integral here, I'm going to come up here and do it, is going to be x e to the x, okay? That x e to the x, that's your uv, minus the integral of your bottom line down here. The bottom line down here is just e to the x dx. E to the x dx. And I think we can do that, can't we? This will be x e to the x minus e to the x, okay? And we'll have a plus c, okay? I sort of don't want to put it in yet, but let's see what happens. So let's write down what our solution is then. Okay. I started writing the answer here but didn't, so let me now minus e to the x. Okay. The x e to the x was the first part. Why I went up here, I don't know. So let me erase this up here. This is getting just too, ooh, it didn't erase. Okay. I didn't need this up here. Well, I maybe sort of did, but I'm going to take it out now. Okay. Okay, the integral of that side was x e to the x minus e to the x. Okay, got that. All right. And I'll go on and put in my constant here. I'm not sure I'm going to leave it c, but we'll put in something there. Okay. Let's call it C1 in case we want to change it. Well, I want to get this for y. Well, what is a y? Multiply both sides by e to the 4th, right? Okay, so this will be y is equal to x to the 4th. That would be x to the 5th, e to the x, minus x to the 4th, e to the x, plus C1e to the fourth. X to the fourth, sorry. Goodness gracious. Yeah. Okay. That then, I think, is your general solution. Okay? Y is equal to x to the fifth e to the x minus x fourth e to the x plus c, and they left off the 1. I thought I would change something, but I won't, so let's just leave off the 1. C x to the fourth. Got it. That's your general solution. Okay. No! This thing won't pick up the... Okay. So that's your general solution. One parameter system. The C is your one parameter. Okay? I'm going to go on and clear out that 1. It's in the way there too. Okay. Okay. All right. Now they have a little blurb right below that. Except in the case in which the lead coefficient is 1, the recasting of equation 1 into standard form 2 requires division by a sub a1 of x. Now if you go back to a couple pages prior, if you got your books, when they first wrote that down, they had a1x, just like we had x in front. And we had to divide by x, okay? Well, when we divide by x, of course, that might have been an issue if x were ever equal to 0. But you know, if x were equal to 0, then our whole problem wouldn't have made any sense, because it would have been 0 dy dx is equal to minus 4y is equal to 0. That's pretty obvious. Y is equal to 0 is the only solution to that. Because, you know, you would have had x 0 there and there. So dividing by x here didn't hurt us at all. Okay? But sometimes dividing by that might introduce a singular point, a value you really can't divide away. So if that's the case, pay attention to it. Don't just do it willy-nilly. Okay? Y'all were out there willy-nillying, weren't you? Okay. All right. Any questions on that? Let's go to example 4. Find the general solution for this one. X squared minus 9 dy dx plus xy is equal to 0. Okay? What would be your first step? Yeah, get it to standard form, and what would you need to do to get that? See, the standard form has just a dy dx in front. This has an x squared minus 9, so we need to divide that out. X squared minus 9 here, divide this by x squared minus 9. And, of course, when you divide 0 by x squared minus 9, it's still 0. Okay? Now, warning, warning, warning. In this case, x cannot equal plus or minus 3 because you just divided by x squared minus 9. If it's either plus 3 or minus 3, you're going to be dividing by 0. So this is one of those situations that this will be two singularities. Okay? You can't have them in there. But we'll just set that aside for now and see what happens. Now this looks like our standard form, where our dy dx plus, and our p of x is x over x squared minus 9 times y is equal to 0. So this is our P of x. And what do we do with that P of x? What do we do with the P of x? If you turn back, you see the first thing you do to it is integrate P of x dx. Right? So that's what we're going to do first. We're going to integrate x over x squared minus 9 dx. All right. How do you do that? Actually, substitution should not do too badly here. Okay, there is another technique, but this will do fine. What will you do? Let u equal x squared minus 9. Then du is equal to 2x dx. We really don't want a 2x dx, we want x dx, so that would be du over 2 is equal to x dx. All right, so we can take this integral, and it now becomes the integral of 1/2, because that 1 over 2 comes out. Your x dx is your du, and your u is the x squared minus 9, right? How do we integrate that? What's that? The antiderivative, yeah. It's the antiderivative of 1 over u du. Log u. That's log u. Okay. X out. We need to get that back to x's, so this will be 1/2 the log of, and you really need to put your absolute values in there, x squared minus 9. Okay. But you can also, just like we did before, do this as log of absolute value x squared minus 9 to the 1/2 power. Right? Okay. Now, that's your integral of P of x dx. What do we do with that? The next little step here is e to that integral. So, e to that integral will be e to the log absolute value x squared minus 9 to the 1/2. And remember what that gives us. E undoes log, log undoes e. So this is merely absolute value x squared minus 9 to the 1/2. That's what that integrating factor, or that's what the e is. Okay? And that is your integrating factor. All right? Now, what we can do here, folks, to keep us from out of trouble and to get rid of those absolute value bars, because I really don't care for them that much. Okay? So what we'll do is restrict our interval to be between -3 and +3. And there's no, that doesn't work, does it? It has to be outside those. Yeah. No. It has to be outside. So it either needs to be less than -3 or greater, and it can't be either of those either, because, plus or -3 either, because you can't take the log of the 0. So that means that this thing has to be positive, okay? Which means that x has to be less than -3 or greater than +3 for this to work. And if we wanted to, we could just arbitrarily say we're just going to take it to be positive, greater than 3. And if we need to, we'll come back and use the less than minus 3 if we need those. But let's just take it greater than 3 and work in that interval only. Okay? I don't know if that's fair to do, but that's what I sort of want to do here. Okay? Okay, I was trying to find where I was. There I am. Okay. Now, and what they do is basically the same thing I was doing, except they don't even give you very much leeway on it. They just say this is the square root of x squared minus 9, wherever that fits. Because the square root is going to be positive, but the thing in there just can't be negative, okay? So that's going to be only good where x squared is greater than 9, which would be x, yeah. So on whatever integral that works, okay? And they do say, they do give these intervals, now that I look at them. That'll be minus infinity to minus 3 and 3 to positive infinity. Exactly like I said, less than minus 3 or greater than 3. It can't be plus or minus 3 because then you'd be taking the log of 0 and you can't do that. So you restrict yourself to one of those two integrals, or intervals, or both of them if you choose. Okay. Oh, okay. Okay. It says P is continuous there. Okay. P is. Okay. But when you take the square root of P, yeah, then you have to eliminate that middle one. We note that we shall solve the equation for the first and third integrals. See, I was eliminating that already. Okay. Because, yeah, it breaks it into that union minus 3 to 3 and this. It just can't be plus 3 minus 3 because of this. Okay? So our whole thing has to be that. But because we're doing a log of this thing, that also keeps it from being either one of those. But the other thing is this thing. Now, as soon as you do the square root thing here, that requires this to be positive. And this is positive only here or here. If you're between minus 3 and 3, this would be a negative number. So yeah. Yeah, it said it's continuous on those three intervals, but we have to throw out the middle one because you can't take the square root of a negative number. Okay. Yeah, I sort of glossed over that. Okay. Now, and the integrating factor is this, and we'll leave that alone. Okay. Now, what we do with that, that's our integrating factor. We will then do the square root of x squared minus 9 times dy dx plus the square root of x squared minus 9 times 1 over the square root. That would be x over the square root of x squared minus 9. Okay, because you're multiplying this, and that's equal to 0. Okay, now we do the magical thing we did before. We note that this is the derivative of the square root of x squared minus 9 times y. Okay, now, I don't know if you buy that, but let's check it and see. Well, it's a product rule. Derivative of this, I think I'll rewrite as x squared minus 9 to the 1/2 power. Okay? So the derivative of this would be 1/2 of this to the minus 1/2. Okay, there it goes. But you have a 1/2 out front, but then you have a 2x, 1/2 2 go out, and you have the x. Sure enough, that's fine. Oh, I left off my y here. Okay, sorry about that. Okay. Yeah. Yeah, left off the y. Okay, and then the other one is this times the root of this, which is that. And that's equal to 0. Okay, so this is equal to 0. Well, this is, you can put your dx over here. Sorry about that. And basically, this just becomes a constant. So the integral of this is the square root of x squared minus 9 y is equal to some constant c. Right? That's what gave. If you integrate 0, you get a constant. Right? Now, so the y then is equal to c over the square root of x squared minus 9. Okay? And again, you see that x can't be plus or minus 3. We already said that. It can't be anything between minus 3 and 3. So in one of those two intervals, that is your solution. Okay. Now, and that's exactly the answer they get. Y is equal to c over the square root of x squared minus 9. Now it says, notice in this example that x equal 3 and x equal minus 3 are singular points of the equation, and that every function in the general solution that is discontinuous at those 2 points. Of course it is. Like I said, it can't be plus 3 or minus 3, because then you'd be divided by 0. So every solution out there would be discontinuous there. Okay? On the other hand, x equals 0 is a singular point of the differential equation in example 3, which that's the last one we did when we were dividing by x. And of course that didn't make any sense, but the general solution is noteworthy that every function in that point parameter family is continuous at x equals 0 and is defined on the interval minus infinity to infinity, not just on 0 to infinity as stated in the solution. However, the family defined on that still cannot be considered a general solution, since the singular point x equals 0 still causes a problem. A lot of blah, blah, blah there. Okay? Just notice that you can't allow that to be plus or minus 3 there, or here, or anywhere. It just can't happen. There's singular points there. You can't have an answer for that. Okay. Let's do example 5. It's all that ink. Goodness, my eye hurts. Let's solve this one. dy dx plus y equal x. Okay? But this time, we've got an initial value. Y at x equals 0 is equal to 4. Okay? So this one, we will not come up with a c. Well, if we get a c, we're going to use that and evaluate it away. Okay. What's that? It's in standard form to start with, so we're hunky-dory with it. So what's the first thing we do? Okay, we integrate the p of x. What is your p of x? 1. And the integral of 1 of dx is x. Okay? All right, and then we raise that, so we have e to the x. That's the next thing we do, right? All right. And that then becomes our integrating factor. So we have e to the x dy dx plus e to the xy, yuck, Wish I could blame that on my eye, but it's just stupidity. Okay. E to the x, y, and that's equal to x e to the x, right? We just multiply through by integrating factor. God, that hurts. All right. What does this left-hand side become? D of e to the x, y, or y e to the x. I think I like it better, y to e to the x, so let's change that around. Just seems to fit better that way. Y e to the x. And this is going to be, you're just going to integrate that side too. So, let's just check and make sure we got this. I always like to do this to make sure I haven't skipped a step or forgotten something. You take derivative of this, product rule, be dy dx, e to the x, that's what we got here, plus y times d of e to the x, which is e to the x, y. Yes, that works, okay? And then this over here will be x e to the x, okay? We're going to integrate both sides, and what does that give us? Y e to the x, because the derivative of an integral of the derivative is whatever's inside, is equal to, we've been there before, haven't we? Remember what that gave us? What's that? Plus e to the x. All right. Plus some c. Okay? And then what we're going to do is solve this by dividing by e to the x. So it will give us a y is equal to, that goes out, this goes out, and you get x plus 1 plus c e. Yeah. Say again? Oh, yeah, minus 1. You're right. Yeah, let me go and correct that. Yeah, I'm sorry. I was going too fast. X minus 1. X, okay, I forgot that one too. There it is. Yeah, because it's integration by parts is uv minus. Okay, yeah, you're absolutely right. Okay, and this will be c e to the minus x, because you divided everything by e to the x. All right. Now, our initial condition says that when x equals 0, this y is equal to 4. So y of 0 is equal to, that would be 0. You get a minus 1 plus c, right? E to the minus 0 is, e to the 0 is 1, yeah. And this is equal to 4. So that means, add 1 to both sides, c is equal to 5. So our answer is y as a function of x is equal to x minus 1 plus 5e to the minus x. All right. Let's see how they did. Y is equal to x minus 1 plus ce to the minus x. Well, ce to the minus x. C is equal to 5. So yeah, y is equal to x minus 1 plus 5e to the minus x. And where is that good? That's good. Minus infinity less than or equal to x less than or equal to infinity on the whole interval. Because you haven't had to divide by any values of x. Everything here is fine, continuous everywhere. So that looks good on the entire interval. Sorry. My eye is hurting like crazy. Of course, I rubbed it a minute ago, and that made it so much worse. But it felt like I needed to rub it, and I shouldn't have. Okay. Now, here was our general solution. This line here is called the general solution, the one with the C in it. That gives you a family of curves, one parameter curves, and when C's are positive, these are curves like this, okay? When C's are negative, they're curves like that, okay? Not particularly easy to see, but when C is equal to 5, it happens to be that curve right there, okay? Basically looks like a slant asymptote almost. It's not. I mean, it is a slant asymptote in a sense, but on the other side, it's just going to infinity pretty nicely. So that's your family of curves. That's not all of them. That's just a few of them. And they picked out the one where C is equal to 5, and that would be that. Okay. Now, one other thing here. If the C were equal to 0 here, okay? If that were equal to 0, that term goes away. Then you have y is equal to x minus 1. That's a straight line that goes through the intercept. Y is equal to negative 1, x equal to plus 1. You know, that's your x-intercept. And it would just be that straight line there. All the other curves, that would be C equals 0, obviously, and C equal positive would be things above it, C equal negative would be the ones below it. Okay? So they threw that in there. We say that CE to the minus x, this term right here, they throw all this stuff in at the end of it, is a transient term. This is the one with C is equal to 0. But when C is some positive value, you're then adding to that a very small amount because e to the minus x is small for positive x's, but huge for negative x's. So therefore, it blows up the more negative x gets, but it goes to the transient, dies out for large x. Now, if C were negative, same thing holds there. As C goes to 0, you're approaching a straight line, and for C anything less than that, you're when C is negative. This thing for large x's, that's going to 0. So your C isn't contributing much there. If x's are negative, then this is a pretty good sized number. Goodness. C is negative, so you fall off and go to negative infinity pretty quickly. That's the ones down here. So, sorry. That glare of the light just really sends my eyes going crazy. So CE to the minus x is a transient term. While this behavior is not characteristic of all general solutions of linear equations, the notion of transient is often important in applied problems. So when you get to your engineering problems and you have vibrations or other things going on with something, heat transfer or other things, if you can get rid of the transient, you usually go to steady state. If the transients are cutting up on you, you don't have steady state very well at all. Okay, discontinuous coefficients, okay? In the applications, the coefficient P of x and F of x in that original equation, may be piecewise continuous. In the next example, f of x is a piecewise continuous function on 0 to infinity with a single discontinuity, namely a finite jump discontinuity at x equal 1. We solve the problem in two parts corresponding to the two intervals over which f is defined. It is then possible to piece together the two solutions at x equal 1 so that y is still continuous at 0 to positive infinity. So let's do that one. Different kind of a problem here. Our f of x is not a continuous function. Okay. Oh man. dy dx plus y, looking good so far, is equal to f of x, looking good so far. Boundary value, or initial value, y of 0 is equal to 0. That's looking pretty good so far. But the problem comes in that f of x is a discontinuous function. It's equal to 1 for any time 0 less than or equal to x less than or equal to 1. Okay? It's equal to 0 anytime x is greater than 1. Okay. Oh my. Okay. So you have to do this problem in two different pieces. Okay? One for 0, x between 0 and 1, inclusive. And then we'll do again for anything x greater than 1. And f of x is 0. Your homogeneous case there. Wow. All right. Where would you begin? P of x is equal to 1. I can handle that. Okay, what's the next thing you do with that? Integrate that. And integral of p to the x, or 1 dx, would be x. All right, I think we can handle that one. What do we do with that then? Raise it to, that is the exponent for e, okay? So our integrating factor is e to the x. So now we rewrite our original problem. E to the x dy dx plus e to the x y, or I probably should have done y e to the x, is equal to, okay, I'm going to put e to the x. This will be this case right here. Anytime x is between 0 and 1, that will be that case. Okay? Then later we'll come back and do the other case. Okay. Now, first I want to make sure that this is what you reckon that product will be. E to the x times y, right? Let's check and make sure that works. Derivative of this would be e to the x times y, there that is, plus e to the x times the derivative of y, there that is. Fine. Okay? So this is equal to e to the x. Now let's integrate both sides. And what do we have? E to the x y is equal to e to the x plus c, right? Okay, I mean, a fairly simple integration. Let's divide both sides by e to the, everything on both sides by e to the x, and that will give us a y is equal to 1 plus c e to the minus x. Okay. All right. We know that y of 0 is equal to 0, so that means y of 0 is equal to 1, and e to the 0 is 1, so that's plus c, and that's equal to 0, so that implies that c is equal to -1. So our general solution here is y is equal to, 1, yuck, I can't write. Goodness gracious, I'm feeling so rotten. Y is equal to 1 minus e to the minus x. Okay. That's any time you're between 0 less than or equal to x less than or equal to 1. Okay? That's your solution for that. And again, your e to the minus x is a transient term. Normally y is equal to 1. It's just that straight line like this, but now we're restricted. Actually, now we're negative. So how that deviates from 1 is 1 minus a pretty small number. No, it can be quite large, I'm sorry. E to the minus of a fractional form, positive fractional form. Okay, e to the minus x, when x is between 0 and 1. E to the minus x looks like this. X between 0 and 1 is subtracting off a fairly significant value. Sorry, my eye is just hurting so bad it's hard to look at the board. Okay, let's forget about that. Let's just go on and do. So 1 minus e to the minus x, anytime 0, x is between 0 and 1. Okay, but we need to go back and do the second part, and the second part is the 0 in there, not 1. Okay? So that is dy dx plus y is equal to 0. This is anytime x is greater than 1. Okay? Everything else is still fine. We're just going to put in e to the x here. So e to the x dy dx plus e to the x y is equal to 0. Okay? All right. And this side over here, just like before, becomes d of e to the x y, and this is equal to, well, if derivative is equal to 0, this is some constant here, right? So that's when we integrate both sides. So we have e to the x y is equal to some constant c. So this will then be y is equal to c e to the minus x. Okay? And we can't plug in x equals 0 because x isn't equal 0 down here. So we wind up with a constant c that we can't eliminate from this part. Okay? Because we could plug it in here because x equals 0 was included up here, but it's not included down here. Okay, so we leave the c e to the minus x there. All right, but what we do with that, and for some reason they call it C2. I don't know why not leave it C, but by appealing to the definition of continuity at a point, it is possible to determine that C2 so that the foregoing function is continuous to x equal 1. Okay, so this is what it is when x is equal to 1. And when x is equal to 1, y of 1 is equal to 1 minus e to the minus 1. Okay? Well, we want this one also to be that at x equal 1. So that'll be y is equal to c e to minus 1 and we want that to equal 1 minus e to the minus 1. Okay? We want value here when x equals 1 to be the same as the value here when x equals 1. So it will be continuous at that point. This is what it is there. So what we do is multiply both sides of this equation, and it's sort of messy here. Set those two equal each other. We don't need the y anymore, I don't think. Okay, so multiply both sides by e. So you have c is equal to e to the 1 minus 1. Okay, so that's our c. So plug that back in. Y is equal to e to the 1 minus 1 times e to the minus 1. Okay? I'm driving myself nuts here, I think. Okay? Which would be, I think that's it. E minus 1 times e to, oh, I'm sorry. This is e to the minus x there. No longer. We're plugging this value c in here, and that leaves e to the minus x. And that's exactly what they get there. So for x greater than 1, we have I just don't have enough room to write. So since we've already used this, let's get that out of there. And we can take this out of there too. So here we have y is equal to 1 minus e to the minus x anytime x is between 0 and 1. And it's equal to e minus 1 times e to the minus x anytime x is greater than 1. It's not defined for e less than 0. It wasn't in our original problem. It can't be now. So this gives you the solution they got. Okay. Now, goodness, my eye hurts. And I don't know if this is helpful to you or not, but it does at least sort of, to me, make sense. Okay? Here is your first derivative function. Okay? There's your f of x is 1 anywhere you between 0 and 1, and then it's 0 everywhere else. Okay? Now, that's your f. When you do this integration here, you have a derivative here. It's discontinuous. The derivative is discontinuous at x equals 1. Okay? And the derivative down here of this function here, this is a positive value, and they have it sort of curved looking, but it really seems like it should be just a straight line. 1. No, you got the y in there too, so yeah, there is a curve. But then you have a discontinuous first derivative there, but you have a continuous function there. So that's why this works out okay here. It's a continuous function. The first derivative is continuous because you have a, what do they call that? Cusp there. First derivative is one thing here, something else there. So yeah, the first derivative is discontinuous, but the function itself is not. Okay? And that gave you your continuity there. Now, yeah, is it time? How can it be? You had to be sad when you told me that, weren't you? Okay, we're just going to make a very brief little comment next time about functions defined by integrals. We have these show up every now and then, and we'll throw one in here for this one too. We almost finished the section, So 2.3, I think you could do any of the odds 1 through 23. And I think you can do any of the odds 25 through 35. And then I think you can do any of the odds 30, either 37 or 39. And I think you can do 41. But you might want to stop there. Yeah, let's stop at 41. We almost finished everything by that point. And we'll pick up the rest of those next time. Good deal. Any questions? Okay.